Hey guys, so we have a lot of topics to talk about today. Hopefully this method of kind of recording voice and drawings is helpful. Give me feedback, that way I know for next time, and I might try to start doing this weekly just to better, help you guys understand concepts. So we'll see how it goes. So a lot of you guys needed a review of the same topics such as SUVs, time of flight, partial volume effect. So we're going to talk about those for sure. I have a list here of everything you said you needed help with. So it's first important to just kind of refresh your mind of how exactly positrons collide and create the annihilation effect that give us those coincidental photons that we image in PET. So this slide really does a great job. What I want to show here is the idea of coincidence timing window. So if I can figure out how to work this. As you can see in this image, it shows that an annihilation event occurred at the little star, and then it shows your two photons going in opposite directions. As you can see in the image, two detectors have been struck. They are within that 90-degree angle of each other. So let me draw that here. So for example, this detector here can interact with any other detector that's in approximately 90 degrees. So this isn't going to be exactly 90 degrees, but any event that is in this angle here, so all of these can interact with this single detector. And that's the same for all other detectors. So if we have this one here that I'm drawing in green, it can interact also with the detectors across from it within 90 degrees. So this drawing's, not too hot, but hopefully that helps you understand kind of how each detector can interact with other detectors that are across from it within 90 degrees. Let's see if I can erase some of this. Good. So now let's talk about coincidence timing window. The coincidence timing window is also called electronic collimation. So remember, although we sometimes have the septa in PET, it's still not technically collimation. The idea is the same basically, but we have electronic collimation only in PET, which is from the coincidence timing window. So what that is that in order for a count to be registered, it has to strike opposing detectors. So example here, this detector and that detector within a set amount of time. The shorter your coincidence timing window, the less overall counts you will get, but that also can degrade your image. So the longer your coincidence timing window, the opposite is true. The more counts you'll collect, but in the image, the resolution might be better, but in turn, you'll have more scatters and random events collected also. So then you'll need to be sure all your settings are correct in order to reconstruct your image accurately. So the average coincidence timing window is between 5 and 15 nanoseconds. That's really, really short. So that is the theory of coincidence timing window, is that it's just the time that you allow opposing detectors to collect events. So since we just talked about the different types of events, I wanted to show this slide to just kind of remind you, and we can talk about it. So in theory, true events are the only actual type of event or count we would want in our image. But we know that's not the case. We do have scatters and randoms. There's another type of event called a single event, but that's where randoms actually come from, is that two photons from singles get detected in detectors that are opposing, and so that counts as a random. You're never going to just have like one photon collected, because it won't create that LOR or line of response, and it won't add anything to your image. Scatter events, as shown in the middle here, is where the LOR isn't actually created in the correct place. It's displaced due to scatter, which we know what scatter is your photon hits a tissue in the body and it gets kind of knocked in a different direction. So a lot of you guys wanted me to kind of talk about what an LOR is in more detail. So let me see if I can draw here with this yellow. So the true is a good example. The red dot is the annihilation, and the black arrows are your photons going in approximately 180 degrees. So that is an example of an LOR. In the scatter event, how it's angled, your LOR is always going to be exactly 180 degrees, so a straight line. So if we had to draw it, it would be more like this. And as we can tell, it's scattered, so it's displaced. Here, this LOR would strike between the two, and that random is definitely not even accurate at all. So your LOR is an imaginary line that is between the two detectors that have detected photons within that coincidence timing window, in which they're assuming the annihilation occurred. So without time of flight PET, it assumes that the annihilation happens somewhere along that LOR. It's not exact, and we're going to talk about the time of flight PET in just a minute. But so just try to keep that and get that, a good understanding of what the LOR is that it's just that imaginary line between two opposing detectors in which both have collected annihilation photons, and it assumes that annihilation happens somewhere between that line. I really like this slide because it kind of gives you an overview of everything that's going on. So it actually looks like a body in the middle of the scanner field of view, also called bed position. I think I have another slide we can talk about that. The little radiation symbol on the image is showing you where the annihilation took place. The little red squiggly lines are showing the two photons, and then A and B shows the detectors that are involved to collect the count. So here you see at the bottom part here kind of two different sections. One's just PET, and then one's TOF PET, time of flight PET. So as you can see, like we just talked about, without time of flight, the probability of the annihilation happening somewhere along the LOR. Remember, the LOR is imaginary between the two detectors. Time of flight PET actually kind of pinpoints more specifically where on the LOR that the annihilation probably took place. It can't get exact due to the randomness of decay and like the light output. It's never going to be perfect, but as you can see here in the peak, it says more than likely it's somewhere right along here on this LOR, which we can tell is pretty accurate. As to where on the non-time of flight PET, it's just saying it could have happened anywhere along here. I see the radiation symbols kind of pinpointed in the exact same place. That's just to show you where it occurred, but your system's not going to store it as saying, oh, that's exactly where it happened, unless it's time of flight, and then that's where this peak comes into place. So it's saying more than likely, that was bad, sorry, right down the middle is where it happened, less likely on the outer. So I think we've probably all taken a probability class where we can understand bell-shaped curve. So just know time of flight shortens your LOR, and it better estimates where the annihilation probably occurred along the line of response, or LOR, between the two detectors. This image is really good for just kind of visualizing what a sinogram is and how it adds to your overall image. So in A, consider that your raw data sinogram. That is your counts collected before any reconstructions have occurred. And B, I don't know exactly which one it is, but we'll just say that scatter has been subtracted out from B. C will say your randoms have been subtracted out. And then D is where reconstruction has actually begun to give you a single slice of your image. So your sonogram is all your data that's been collected from one bed position or one field of view or set of rings, that 360-degree rings around the patient at a single time point, and it creates one single slice. So without getting too technical, that's what you really need to know and understand for your sonogram, is that it represents a single slice of data, and sonograms get stacked and stacked and stacked, literally millions of them, and they create your image in PET. So sonograms can add information such as voxels. So if you think of that as a 3D pixel, just like SPECT, that's how you get that 3D image that can be seen in different formats, different slices and angles. So that's how PET can be viewed through like sagittal, transverse, coronal images, unlike other I guess just normal gamma camera images. So SPECT does the same thing as PET, where you can see it kind of in a 3D setting, and that's because of all the sonograms contain 3D information once they're stacked up. I think I have another slide too that is going to show a different kind of point of view of this, but just be sure to read about sonogram so you can kind of understand what that contains as far as your raw data. This image is super helpful also to kind of show you the idea of a bed position. So don't get too confused on what a bed position is. It's quite literally the position that the table or the bed this on the scanner is in at that moment. So basically where the table is underneath your crystal rings. Bed position is also your field of view, so where exactly you're collecting your data or your counts from at that moment in time. All scanners are different with how large their field of view is or their size of their bed position, but pretty standard is that everybody's brain can pretty much fit in one bed position. Everybody's heart can fit in one bed position. And those are the two main organs that can be imaged in PET in just one simple bed position. So if you look in this image, it gets a little technical. It says detector 1 and 2 in the TOR, so where it's actually collecting counts. What I wanted you to see here was this ring. Whoops, let's see. So if you see the ring, consider it 3D, and that's your bed position there. So two of the other ideas or topics you guys wanted me to kind of cover, I couldn't find the best images to kind of show these things, so I just figured I would type these quick notes out and we'll discuss them. So SUVs stand for standardized uptake volumes. There's a few other like nicknames for them, but this is what we'll refer to them as because in Memphis in our clinical settings, that's what they're called. And that's how all PET reports that you'll be able to see also call them too. So once you guys get out to your PET clinics, you'll be familiar with them being called SUVs. So anyway, SUVs are a measurement tool that your radiologist can really use to see if things have changed in the body or how much activity is concentrated in a certain organ or a region of interest. So it might not even be your entire organ you're trying to figure out how much activity is in. It might be like a certain lobe of your lung, or it could be a certain section of your stomach, or whatever the case may be. You can really do an SUV value anywhere in your body. So SUVs, there's a formula. You don't need to know the formula per se, but I want you to know what is included in the formula. So that involves the concentration of your injected activity. So keep in mind your concentration is like your activity millicuries over your volume. And then you need to know your patient's body habitus and weight. So that can be grams, it can be kilograms, it can be pounds. You can use anything as long as you keep it uniform and know how to convert, but you need to know your patient's body weight, and then you have to know the measurement or how much activity or concentration is in your region of interest. So that's where you would have your tumor or wherever you're measuring. So let's take a turn. If you think of a HIDA scan, how after the gallbladder's filled up and you manually go on there and you click and you draw your ROI around the gallbladder and you get that measurement, it's kind of similar here, except know that we can do that anywhere in the body. SUVs are really mostly or only used, I won't say only, but mainly used in F18 FDG PET. So this second half of our course is really mostly about F18 FDG PET. So we're going to talk a lot more about SUVs, in a few weeks. Another key point that I want you guys to know is that SUVs that are greater than 2.5 might indicate malignancy. Also, if you have your injection sites infiltrated, the SUV could be super, super high. In that case, they can tell that that's not malignancy, but you want to be careful of where you inject. You want to make sure your injection's good, because if your lymph node is over 2.5 on the same side that you had an infiltration, they honestly might not know. So that's another, just to kind of review of why it's important to have good, proper injections. But anyway, so just keep in mind, SUVs greater than 2.5 might indicate malignancy. Not always, but they might. Some SUVs can get as high as 18, 19, 20. I feel like I've seen in my clinical experience way higher than that. But, and some are less, and they still might indicate malignancy. It just depends. One good thing that SUVs are being used for is a patient's baseline PET scan. So when they're first diagnosed with cancer, they'll come in and get a baseline PET scan. They might go through treatment, radiation, chemo, immunotherapy, whatever their treatment is, come back in a few months for their PET scan, measure those same areas or regions of interest to see the SUVs, and then you want to see how the SUVs have changed. So that can indicate a positive response. It can indicate no response. It can indicate progression or worsening of their cancer or oncology disease also. So SUVs are very, very important. To kind of shift gears a little bit, attenuation correction. So in your book, and I know in PowerPoints that I've made, it talks about a rod source that can spin around the patient and create an attenuation correction map. You're not going to see that anymore, so just kind of know that was the history of PET technology, but that's not around anymore. So be sure to focus on CT attenuation correction when you're studying and when you think about PET. So the CT scanner is just like you guys are learning about in your CT course now. It's the same thing. It's a lower dose. All your settings on CT are less. That way your radiation dose from the CT isn't as high. We'll talk more about dosing from the patient, how much radiation dose the patient gets from PET CTs later in the course. But just know that you collect a CT scan of the same part of the body you're imaging for your PET. So if that's from head to toe, if it's from your forehead down to your thigh, or if it's simply just your brain, you're going to take a CT scan of that same part of the body. And then that data is collected in Hounsfield units, and it represents different attenuations throughout the body, as you guys are probably learning about in CT now. That info is converted into 511 keV data that matches your PET data. So that's the key point I want you guys to take away here, is that the CT info is converted into PET coefficients. That way they can be laid on top of each other and it all registers together. So the attenuation correction data creates a map and it's laid over the PET data, and that helps during reconstruction. So that just literally takes into account that different parts or different tissues of the body absorb some of these photons, and then that degrades our image. But with the CT attenuation correction, we can get a much more accurate image from the patient's body. So the last few topics you guys wanted me to cover include quality control or QC, the partial volume effect, and then reconstruction. So for quality control, the main thing you need to know is, or to understand, is why we do QC in PET. We want to make sure there's so much hardware and software in PET. We really want to make sure that everything is functioning. That way we can get all of our counts. We can get all of our data to be reconstructed correctly, and for the image to be the most accurate representation of how the tracer is being processed throughout the body and where the radiation or annihilation reactions are actually occurring. So every camera you might work with requires a daily blank scan. So typically you'll put a little rod source that has a very small amount of activity in this little plastic holder, and it will set in the camera, and it'll sit there for about maybe 45 minutes or so, and all the detectors will be on, and they'll be trying to collect as many counts as possible. And then you'll be able to run a report, and you'll be able to have a visual image to make sure that you can check that all of your detectors work. You're getting the correct amount of activity calculated, because we know how much activity is in that rod source. And so it's really just to check and make sure your system is working before you scan a patient. And then your system automatically will adjust for the PMT gains and other things it has to adjust for automatically when you do your blank scan. And then all the other QC tests are really variable based on manufacturer. Most of the other tests just get really specific, and they're testing each part of your system. So they might test your ability to subtract randoms and scatters out of your overall image. It'll test your light output for your crystals. It'll test that your energy resolution is correct. And to be quite honest, your system manufacturer, the technician or the engineer typically does most of these tests for you, because it's included in the contract. So it's good for you to know why they're doing the test. As far as how to do them, I would just say read your textbook and see what all information it offers you as far as that goes. For testing reasons, don't focus too heavy on that. Just really know about blank scan, understand normalization. That's real, and know how often each test is performed. So as far as the partial volume effect, that's really a concept that plays heavily into the SUV values. So as your ROI gets smaller, the measurement or the ability to measure your SUV is not as accurate. So of course, if you have a very tiny lymph node in a patient, and you might not be able to accurately measure the SUV value as accurate as you would a huge swollen lymph node. That's just one example. It's not only to lymph nodes, it's anywhere in the body. So the smaller your region of interest, the harder it gets to accurately measure the SUV. There's great information in your textbooks about this, so I would look. There's a lot of images that kind of show how there's a phantom with these different circles that are varying in size, and they all contain the same amount of concentration of activity. So therefore, when you measure it, it should have the same SUV. However, as you get smaller and smaller, that SUV becomes less and less, because your system just cannot, quote, see the accurate amount of activity in that part. So be sure to refer to that. And then as far as reconstruction algorithms, it's just really important to know that if your system is working correctly, you're gonna be able to correct for scatters, randoms, and delayed. So delayed events are those events that struck beyond your coincidence timing window. So say your coincidence timing window is set at 15 nanoseconds, but you have a count that comes in at 20 nanoseconds. So it's not correct. It's not included in your actual image. But there is a way that they can kind of adjust to say, well, that might have, been a true count that we might need to consider. So it's just a small proportion of those that might add to your image. In PET, we also use iterative reconstruction, filtered back projection, OSEM, just like spec systems do. So I would highly recommend reviewing that. And I have a video that was provided to me by the Society of Nuclear Medicine. I have a friend that I was able to email and say, hey, can I get this video you guys have for my students? And so she was super nice and gave me those videos. She actually gave me a whole series. So they're helpful. They're very well put together. I think they'll help you guys a lot. I will upload it right now when I upload this video. And it basically goes over the same exact things that'll be on your exam 1. So instrumentation, it'll really help you guys. So don't stress too much. I know I gave you your study guide. I am here to answer any questions you may have. So your exam will be on Wednesday. Your further details on your exam are to be announced, but I'll let you guys know no later than Tuesday. So email or text me if you have any questions, and I'm definitely here to help you. Thanks. Bye-bye.